position, if we want to write for position relation, what we can do is, since displacement is change of position, we can write x minus x naught as ut plus half at square. So x can be written as x naught plus ut plus half at square. So you can write it like this. Means the initial position plus displacement will be the final position. So you also have question based on this. V equal to at plus u. So what we can do is we can put time equal to v minus u by a. So if you replace this time in this expression, the s will be u, and at place of t you can add v minus u by a, and here you can have a by 2 v minus u by a square. So if you solve it, we will have v square minus uv by a plus v square plus u square, then minus 2vu divided by 2a. So if we solve it further, 1 by 2a, and if we solve it further, we will have v square minus u square and by 2a. So it will be v square minus 2u square equal to 2as. So let us check it again. So that is u square. Sorry, this one is uv minus u square. So if we solve it, we are going to get this thing, and finally we have this relation. So this relation you can get it by this, but I am going to discuss another method. Suppose we know that acceleration is alternate method for deriving this. Suppose we have acceleration equal to dv by dt. We can write this dv by dt as dv by dt into ds, and here also ds, and this can be written as a ds. ds is what? Small displacement, and dv, and ds by dt here, that small displacement by small time, this will become velocity. ds by dt becomes v dv, and if we integrate it, this becomes as, and here it becomes v square by 2, and you can put it limit. You can put the limit. Suppose initial velocity was u and final is v. You can put it like this. So we can write it like as v square minus u square by